So greetings. So in this lecture, we're going to talk about approximating the area under curve using right endpoints. In the last lectures, we talked about approximating using left endpoints. It's going to be almost exactly the same, but I want to go through it properly so you can see a little bit how these actually are different from each other. So I won't spend as much time explaining things in this one because you've seen this before. In fact, we're going to use the same function as we use for the left endpoints. We're using the same interval we use for the left endpoint. And again, 5 subintervals. So just like before, we're going to go ahead and graph this. Okay. And then the graph of our function looks like something like this. Let's try to... So this is going to be y equals x squared plus 1. That's a function we want to find the area underneath because that's what we're going to be doing. And then we look here and we say, what's our interval? It's minus 1 to 1.5. So we'll write that on here. So this is like minus 1. 1.5 is maybe more or less here. And then because we wanted to divide it into 5 subintervals, we do like we did before. We can find our delta x. So the first thing we kind of want here always is our delta x, which is going to be the width of a subinterval so that we can figure out where those lie. So here we go. So how do we do that? Again, the entire length is 1.5 minus 1. So that goes on top. So we take 1.5 and then minus 1, and those are coming from there. We need to take the difference between them to find that length of that long interval. And then we remember we want to chop it into 5 pieces, so we divide by 5. And we already know, because we've done this example before, this is just 1/2, or 0.5. So now we go ahead and we write those in. So I keep on adding 0.5 all the way until I hit there. That's how we do this. So we take, minus 1 plus 0.5. So that takes me to minus 0.5, or 1/2. Could write it either way. I add 0.5 again, I get 0. I add 0.5 again, I get 0.5. I add 0.5 again, and I get 1. So now I know where I'm dividing this up. But now this is where things get a little bit different. And again, I'm reusing a color. I know it's the same as that one. We're not going to worry about that. Okay, instead of going up to hit the graph of my function on the left-hand side, I'm going to go up to hit the graph of my function on the right-hand side. So let's go ahead and do that. On the right-hand side of the subinterval, I hit it, I go over, and I go back, and this is going to be my first area. And then we emphasize something that we remember. What does this point look like? Its x-coordinate is minus 0.5. Its y-coordinate is actually going to be what happens when I plug that function into there. Or plug that into my function like that, which is what would tell me that actually this height here, so we already know that this is delta x. But this height, right, is going to come from this here. So this is going to give me this height here. So I'm going to get that this height here is going to be f of minus 0.5. Okay? So that's going to be helpful as we go through to kind of remember that that's how these things work. And then we go on the right-hand side. And we go up until we hit the graph of the function. And then we go over. So this is A2. Up until we hit the graph of the function, and we go over. So this is my third area. But now we're doing on the right-hand side, up until we hit the graph of the function on the right-hand side, and we go over and down. This is my fourth area. And then up until we hit the graph of the function on the, I'm going to move this over slightly. It's okay. Let's just move it over here so that I actually have some function there. Okay, it's always good to, you can adjust your pictures after just to make it work out a little better. Okay, they're just pictures. Over, up, and over. Okay, so this is actually the area. This is the red area is going to give us the area that's going to be our approximation. So let's go ahead and write this out. So our approximate area How do we do this? So again, we just drop these down. So this is going to equal A1 plus A2 plus A3 plus A4 plus A5. And now when we're figuring those out, we realize that, wait, A1 actually came from my height on this side, on this right endpoint side, instead of on my left endpoint side. So I start with 0.5. Okay, so this is going to equal f of minus 1/2 delta x plus f of, again, it's on the right hand side, so it's 0, f of 0 delta x plus f, again on the right hand side, so this is 1/2 delta x plus, and then we keep on going. So f of 1 delta x plus f of 1.5 delta x. Right? And then when we kind of write that all out, that's going to give us, well, you could go ahead and compute these. I'm not going to do it in front of you right now because we kind of did it with the other side, with the left endpoints example. So this is this times 1/2 plus, and then we're going to get here 1 times 1/2 plus, and then f of 1/2 is going to be 5/4 times 1/2 plus 2 times 1/2 plus 13/4 times 1/2. And then I could go ahead and compute that, and I would get out 35/8. Right? And we could remember we can pull the 1/2 out, just like in the other circumstance. And so then what is our general formula? So this is our L5. So this is our L. Oh, no, this is not our L. This is our R. Because we're doing the right-hand side. So R tells us that we're doing the right-hand side. So this is our R5. Okay, and here's our more general formula. Just looking at how we did that here, we can see this. So this Rn is going to equal, so I'm going to start with f of, and then we're doing these intervals with the same notation as we kind of did before. So this is going to be my f of x1 delta x all the way up to, now I'm actually going up to f of x, and this is where this is slightly different than in the other circumstance. Okay, and this is going to equal the sum, and then in my sigma notation, I can pull out the delta x if I want. So this is equal to delta x times the sum from j equals 1 up to n of f of xj times this delta x. Okay, so that's how we more generally do this. So we kind of, to recap, we're going through exactly the same process before, where I'm looking at, oh, I want to get back my original function. I have a graph of a rate function. I know that it's going to actually give me the area under that curve. Why do I know that? Well, I can at least know that if I can do that in approximation, because I know that this is how it works in terms of multiplying a rate times a time in order to get the quantity, which is the same way as we get the area of a rectangle. So we understand how we do that on each of these. We add them up. That kind of approximates our curve. So what we're going to want to do in the end now is we're going to want to make these intervals smaller and smaller so our approximations get closer and closer. And then we're going to say, okay, well, I'm allowed to do this as long as I get the same thing as I do this on the left and the right hand sides. And then in that circumstance, I'm going to call this an integrable function, and that limit is going to actually give me the integral. So we did this for the left, we did this from the right. A key difference to keep track of was, because I'm starting on the right hand side, I don't take this one into consideration. But I took it into consideration on the left-hand side. So we're losing that term. And then we have the situation over here where we gain a term, because when we were taking left endpoints, I would have taken this side. I would not have picked up an f of 1.5, okay? So this is where, but now I do because I'm looking at the right-hand side. And this is why we pick up a term of f of 1.5. We drop a term of f of minus 1. Sometimes students look at them and they aren't exactly sure where that's coming from, and that's where it's coming from. So I wanted to highlight that. But everything else is the same as when we did the left endpoints. So I hope this makes sense, and I'll see you in the next lecture.